So our next talk is by Aram Harrow, and the technologists promise us that he's going to appear. There he is. Hi, Aram.
Hello.
Hi. So, Aram, you are being seen by everyone in the room, and you can.
Great. I see some of it.
Okay. So, how am I going to be able to signal you that you're going over time? Can you? You can't see me, can you?
No, but I can hear you.
Okay. Then I'll have to say. I'll be verbal. Go for it.
Okay, so I have half an hour, right?
Yes. Yes.
So normally I love to be interrupted by questions. I might not be able to hear questions unless you use a microphone. So we'll see how that works. Do you see my slides?
Yes.
Great. Okay, so I'm going to talk about the same work that Elizabeth talked about, but I'm going to give a different perspective on it. I'm going to talk about kind of more broadly what our goals are for this project, what we think are the relevant structures to look at, and talk a little bit about where we think we might be able to go from here. And I guess the sort of broader question that we're interested in is this question of quantum supremacy. We'd like to demonstrate, to do something with a quantum computing device that is out of reach of classical computers. So there are a number of things we want to do here as theorists. We want to come up with algorithms that are feasible for quantum computers, and at the same time, hard for classical computers to simulate. And ideally, they would also be easy to verify that our quantum device actually did the thing that our theoretical calculations have shown is hard to simulate. And if we really want to be ambitious, then maybe they could even solve a useful problem while we're at it. So that's kind of the broader goal of a lot of algorithms work. And a few candidates are factoring, performing low-depth circuits, maybe random circuits, which the Google group is looking at, boson sampling, something called instantaneous quantum computing by Shepard and Bremner, something called the quantum approximate optimization algorithm, or the adiabatic algorithm. And let me kind of talk generally about how these stack up. So the first example, which I kind of for a long time I think was what people had in mind when they thought about a quantum computer doing something demonstrably beyond the capabilities of classical computers, was the Shor's factoring algorithm. And it's worth thinking about this because it has all the desiderata of a good quantum supremacy experiment, except that it's a challenging experiment for a quantum computer. So in the first column, I'm talking about difficulty for quantum computing. And this is a hard challenge for a quantum computer because to factor a number that's beyond what we know how to do classically, you need quite a large quantum computer. And even to get one of a non-trivial size, you need to do it's a pretty difficult experiment. On the other hand, the hardness assumption that we need to rule out classical simulation is one that is pretty mild. It's not that P is not equal to NP, but we have to assume that RSA is secure. We have to assume that there's no good classical factoring algorithm. And this is something that people cared about before quantum computers came along. People have worked hard on this problem, arguably for thousands of years, and you never know. Maybe a breakthrough will come tomorrow. Maybe the NSA already has one. But it's one of the better studied problems, one that we can be pretty confident that there's no good classical algorithm for. It has the further advantage that you can check that it got the right answer. You can pick two random primes, multiply them together, put them into your factoring algorithm, and then you can verify that it spits out what it's supposed to. And of course, it's also solving a useful problem. So this is sort of the prototypical quantum supremacy candidate. And because it's such a difficult experiment to do, people have been looking at whether you can do whether there's a simpler experimental platform that can lead to quantum supremacy. And there are a number of works that are based on the assumption. There are kind of two ways of saying this. One of them is that the polynomial hierarchy is infinite. Another one is that exact counting is not the same as approximate counting. So let me explain what that means. The polynomial hierarchy being infinite is a conjecture that's similar to P not equal to NP. It's like, I'm not going to precisely explain the difference, but it's similar to that. Approximate counting being different than exact counting means that two tasks, both beyond the reach of polytime algorithms, should themselves be different in complexity. Approximate counting means if you have a 3-sat instance, approximating to within a factor of 2 the number of satisfying assignments. So, are there more than 1,000 or fewer than 500 satisfying assignments? Whereas exact counting means exactly determining the number of satisfying assignments. And again, it's a plausible assumption from complexity theory, and crucially one that does not involve the word quantum anywhere in it, that these two tasks are very different in power. And if you believe these are different in power, then all of these simple quantum algorithms become hard to simulate. So boson sampling becomes hard to simulate. Low-depth quantum circuits, that means that you apply a series of gates, and each qubit only participates in, say, a constant number of gates. There's the AQC by Shepard and Bremner, this instantaneous quantum computing, and the quantum approximate optimization algorithm by Farhi, Goldstone, and Gutman. All of these become hard to simulate under this very plausible complexity theoretic assumption. On the other hand, there are a few drawbacks. So we don't know how to efficiently verify that if we have a device doing this, that it's doing the right thing. In some cases, we can verify some aspects of it. So maybe for the quantum approximate optimization algorithm, we can look at how many, at what value of the objective function is achieved. Or for random circuits, we can check that some of the moments of the distribution that come out are the right thing. But it's not as strong a verification as we get for Shor's algorithm, where if you see a 10,000-bit number being factored, then you really are convinced. And finally, many of these are not actually useful problems. So boson sampling samples from a distribution proportional to the permanence of some matrix. That is hard to do classically, but it was not something that we were clamoring to solve before quantum computers came along. The main utility would be just this demonstration. And of all of these, the quantum approximate optimization algorithm has a chance of being useful in that it actually does give a solution to a combinatorial optimization problem, which may be beyond the reach of classical computers. The last row of this table is, of course, the theme of the conference is adiabatic optimization. And I say that this, like boson sampling, are easy in that they require capabilities that may not be universal for quantum computing. Whereas the moderate column refers to things that are universal for quantum computing, but you just need a short amount of coherence time. So this can really use an architecture which does not have universal quantum computing capabilities. But everything else we're not quite sure about. So whether there's classical simulation is really an open question. Whether you can verify the solution really depends. If you find the exact, if you find the solution to a 3-sat instance, then you can verify that it's satisfiable. But otherwise, if you achieve something less than that, you may not be able to verify it's doing the right thing. And that's where it's useful. Again, that depends on whether it can solve hard combinatorial optimization problems better than classical computers. So this is kind of the overview of our quest for quantum supremacy. So let me talk specifically about the adiabatic algorithm. I think this slide is one I don't really need to explain in this conference, but I just want to say briefly that I'm going to focus on the one as originally proposed. I know adiabatic means something much more general. It can mean non-stochastic. It can involve noise. I'm going to focus just on the simplest cases originally described, where the Hamiltonian interpolates between all sigma x's and between a diagonal Hamiltonian. And I'm not going to consider noise or non-stochastic terms. So when I say the adiabatic algorithm, this is what I mean. And just realize in the back of your head that of course, there are more general versions out there that are being discussed. I want to briefly mention something I've worked on with Eddie a little bit, the quantum approximate optimization algorithm. So also because this is almost like a gate version of adiabatic in some ways. So you start with a uniform superposition. The adiabatic algorithm would say that you interpolate from one Hamiltonian to another one. You start with h sub x and you interpolate to h sub f. Instead, if you apply them in alternating pulses, you get the QA-OA. And you do this p times, and then you measure in the end and see what you get. And what you can show is that this, if you take p to infinity, this includes the adiabatic algorithm. And we know if you run that for long enough, you can get the exact answer. So you can exactly optimize with this. But what's interesting about it is a case when p is small, where we don't think that in general it may get the optimal answer, but in many cases it may get a good approximation. And Eddie and his co-authors have proven that this does give good approximations in some cases when p is small, and also it has some good noise resilience properties. And in some cases, this gives a, you can even bound the approximation ratio. And there have been periods when this has been better than any known classical algorithm. So I think initially the approximation ratio was the best known for some problems. Then classical people realized that the quantum algorithm was beating the classical algorithms, worked harder and improved the classical performance. Then the quantum algorithm was improved. Currently, they're close to a tie, and it's open question whether a better approximation ratio can be achieved by this. But I think it remains a compelling heuristic for combinatorial optimization. So what and so this, like some of the other things in that column, are hard to simulate unless the polynomial hierarchy collapses and unless approximate counting is equal to exact counting. But what I want to talk about is the last column, which I think is, to me, is the most interesting because of all the question marks, because we're so unsure about the power of stochastic ground state adiabatic optimization. I think it's worth investigating. So I would say that the possibilities for this range from very pessimistic to very optimistic. The most pessimistic possible is that there's a classical simulator that always runs in time at most a polynomial of the time required by the adiabatic algorithm. In other words, only polynomial speedups are possible. Now, we know that you can get at least a quadratic speedup with adiabatic optimization via a Grover type speedup. So we know, linear time simulation is ruled out. The best, sort of the most pessimistic thing would be that there's a quadratic simulator. And there's some evidence in favor of the pessimistic scenario, which is that there is this quantum Monte Carlo algorithm, does not work for simulating general quantum circuits. And even though we don't know how well it performs for adiabatic, at least there's an algorithm. At least there's a candidate algorithm to simulate adiabatic evolution. The optimistic side would be maybe that stochastic adiabatic evolution is universal for quantum computing. And this is probably too optimistic. It turns out if this were true, it would lead to these unlikely scenarios. A polynomial hierarchy would collapse. Approximate optimization would be just as powerful as exact optimization. Things that are considered to be unlikely in terms of outcomes for complexity theory. But that doesn't mean we could have something just short of that. For example, I don't know of any evidence against an adiabatic algorithm for factoring. This could well exist, and I would say this is on the optimistic end of the power of adiabatic quantum computing. And whenever you hear a pessimistic and an optimistic scenario, it's tempting to believe that the truth lies somewhere in between. And perhaps it's true that adiabatic evolution gives you exponential speedups, meaning that there are things that cannot be simulated classically without exponential slowdown, but still cannot do everything that general purpose quantum computers can do. There's some evidence for this in terms of a paper by Nagai, Soman, Kirfarova, which is adiabatic, but sort of. It leaves the ground state for part of the time. So it may or may not qualify and gives you an exponential speedup with an oracle. Some further evidence is that quantum Monte Carlo sometimes seems to take exponential time. So that seems to, if our only good classical simulator takes exponential time, then maybe all classical algorithms do. So I want to talk more about the possibility of simulating adiabatic evolution with quantum Monte Carlo. Let me talk specifically about the map from quantum to classical. You kind of saw this in Elizabeth's talk, so I won't dwell on it. Basically, the quantum partition function can be mapped to a classical Hamiltonian with the same partition function. And the way you obtain this classical Hamiltonian is you take one little Trotter slice and you break up the Hamiltonian into diagonal and off-diagonal parts. And these correspond to different terms in the classical Hamiltonian. So a classical example of this is the 1D transverse Ising model. That's a quantum Hamiltonian, which gets mapped into a 2D classical ferromagnetic Ising model. And so if you have over here these 4 quantum spins, this becomes a 4 by L grid of spins with 2 types of bonds. We have vertical bonds are kind of the new thing introduced by this, and they're ferromagnetic with pretty high energy. The energy is on the order of L over gamma. Gamma is some measure of the X field. And what that means is that each bond has probability of disagreeing that scales like gamma over L. So if you think of gamma as a constant and L being large, that means that most of the bonds agree. The total number of disagreements is some constant in gamma in the entire column. So mostly these columns are all the same, but there's a constant number of flips. Then we also have the horizontal bonds, which correspond to the diagonal Hamiltonian. So the diagonal part of that Hamiltonian kind of gets applied to each row, attenuated by this factor of 1 over L. But they're L rows, so once you add it all up, you get back the original energies. So this is how you turn in general, a quantum Hamiltonian into a classical one. And as Elizabeth talked about, the kind of standard component of quantum Monte Carlo is that we use local moves. Of course, it could be world line updates, something more complicated, but some kind of updates to generate samples from the joint distribution. And this is the part we don't know how well it runs. Then once you can sample, it's easy to reduce this to counting, to estimate the partition function, estimate the values of observables. That part is relatively standard. The hard part is to show that the Markov chain corresponding to your local updates converges rapidly. And what this Markov chain looks like is you have all the configurations of your classical system. So a configuration looks like a rectangle of n by L bits. And a move, so I'm not going to consider world line updates, but you can modify this to do that. A move might consist of flipping one bit. So go from all zeros to a single one, and this gives you a giant graph over all the possible states of your classical system. And it's weighted according to the prescription from quantum Monte Carlo. So the weight is going to be given by the average energy of these rows. So you get an exponential factor from that. And also you get a factor from every jump. So every jump in the vertical direction from 0 to 1 costs you some factor of beta gamma over L. And so there's sort of this cost to putting in too many jumps. On the other hand, entropically, it's favored to have some jumps, and so there'll be typically some balance between these. And the question is whether this is rapidly mixing. And so this relates to the question of whether quantum Monte Carlo can simulate adiabatic evolution. And I should mention that for this to be possible, there's a few things that we kind of know will be necessary. So, I wrote the gap is greater than. Less than. Let me make that greater than. So this should only work if the gap of the quantum algorithm is at least 1 over polynomial, and this is because quantum Monte Carlo has this inverse temperature parameter beta, and beta needs to be at least 1 over the gap for the thermal state to be close to the ground state. And beta tells you the number of imaginary time steps. This length L is going to depend on beta. So if the gap is too small, then we won't even be able to get a good approximation of the ground state, even if these things mix rapidly. Also, this will only work if we follow the adiabatic path. Or rather, we should expect that our algorithm, maybe in some cases doesn't need to follow the adiabatic path, but generically it should. Because otherwise, if we could just jump to the end, we could solve NP-complete problems. Since we know at the end of the path the gap is large, if we could just jump there and do something that only depended on the gap, that'd be too good to be true. Is there a question?
No, Aram, it's a question for me, Eddie. You have turned off your slides. We like looking at you, but we want to also see your slides.
Thanks. Let me do that. Hold on. Good. Do you see the slides are up now, right?
Yeah, you're back. And while we're at it, you have 12 minutes. 12
minutes. Great. Okay, and so we should follow the adiabatic path. Otherwise, it would give us something too good to be true. And if you look at my paper with Elizabeth, the place where we use this is as a sort of warm start, to mean that when you start sampling for a given value of the adiabatic parameter, you have something which is not too unphysical. The configurations are not too unlikely. It sort of looks reasonable in many ways. And Bravi and Turhal did something similar in a paper of theirs from about 10 years ago. And of course, even then, there's some arguments that there'll be maybe topological obstruction. So Hastings and Friedman argue that if the quantum state space looks like a circle, then the classical state space looks like strings on the edge of a cylinder. And these can have winding numbers, and it may be hard to transition from one winding number to another. This is something which I think has been underexplored and would be worth looking into more. So Okay, so what I want to talk about is how quantum Monte Carlo, to understand how quantum Monte Carlo performs, I want to talk about the measure over paths that we get when we run quantum Monte Carlo. And there'll be a talk tomorrow by Zhang Jiang, which will, I believe it's tomorrow, we'll talk more about this. So the idea of quantum Monte Carlo is to do a random walk on the hypercube. So you have these classical configurations, bit strings, Z1, Z2 through ZL. Each one is an n-bit string. Typically, it's conditioned to return, so ZL plus 1 is set equal to Z1. We can also use open boundary conditions, in which case you wouldn't have that constraint. And the typical number of jumps will scale roughly like n. So even though L might be quite large, most of these are equal to the next one, and the number of jumps where one bit changes only scales proportionally to n. And to get some intuition for this, let's focus on the bit symmetric case, the case where the objective function only depends on the Hamming weight. And so then we can consider, instead of looking at n-bit strings, we can just look at this as a walk over Hamming weights, which ranges between 0 and n. And let's further assume that this function is continuous. So let's just replace 0 through n. Let's rescale that to be a number between 0 and 1 and make it a real number. And in that case, if we do a random walk on the hypercube, what that looks like in terms of Hamming weight is this kind of Brownian motion. And if you want to do Brownian motion with closed boundary conditions, meaning you return to where you start, it's something called the Brownian bridge. But most of your intuition about Brownian motion can carry over to this case. And if we want to add local z fields, we get something slightly different. We get a drift. We get that it favors not Hamming weight 0, but there's some particular Hamming weight that it prefers. I'm sorry, not Hamming weight n/2, but there might be some other Hamming weight that it prefers. And if you get too far away from this, then you drift back to that point. And so this kind of looks like a harmonic oscillator with friction, something called the Ornstein-Uhlenbeck process, or if you want to condition on returning to where you start, the Ornstein-Uhlenbeck bridge. I'm kind of mentioning this for completeness, but to give intuition, I'm just going to talk about Brownian motion. So even though there are z fields, for the purpose of what I'll talk about next, let's ignore those. Okay, so how can we analyze the Brownian motion that we get with quantum Monte Carlo? One important thing that we'll need to deal with is the local time, which means the amount of time that Brownian motion spends at a particular point x. For the problem that Elizabeth talked about, we want to know how long does quantum Monte Carlo sit on the spike. And essentially, this is a question of local time. How long does Brownian motion spend at a particular point x? And there are a number of beautiful theorems that characterize the distribution extremely sharply. So there's something called Levy's theorem, which says if you look at the local time at the origin, so where the Brownian motion starts, this has the same distribution as another process, which is you take a different Brownian motion and you look at its supremum over time. So in other words, the largest value that Brownian motion has ever reached. In fact, there's even a stronger statement, which is if you look at S minus B, so the supremum minus a Brownian motion, together with the supremum, this has the same distribution, that's what equals D means, to the pair of the absolute value of a Brownian motion along with the local time. And another fact is that the supremum has the same distribution as the absolute value of the Brownian motion. So all these seemingly complicated objects, you can really exactly write down their distribution. And there's a nice proof in terms of random walks. Brownian motions are like the continuous version of random walks, and sometimes it's convenient to go back to random walks to get a sense for how they work. So let's consider a random walk W, which is just a sum of n plus or minus 1 random variables. Okay, so x1, x2, x3 are just randomly plus or minus 1. W of n is where you end up after n steps. And let m be the maximum of this after these n steps. So there are a few observations. The first is that if you look at m minus w, so in other words, the maximum of the random walk minus your current position, this itself is a random walk. Because let's say that maximum minus the current random walk is 4, and you take 1 step. Well, you'll either move up or down. If you move up, then the maximum minus the current value will go down to 3. If you move down, maximum minus the current random value, will go up to 5. So wherever you are, this maximum minus your current value will just follow a random walk. It'll go randomly up or down, unless you're currently at the maximum. So if m equals w, so that you're currently at the maximum, m minus w is 0, you obviously cannot go below 0. So then you will either take a step 0 or take a step of +1. So it's like a random walk with a reflecting boundary at 0. So it's like you take a random walk, except when you hit 0, you have a half chance of staying there and a half chance of going to +1. So this argues that m minus w is distributed roughly as the absolute value of a random walk, because that's what a walk with a reflecting boundary looks like. It's just like taking the absolute value of a random walk. And furthermore, the maximum value m is equal to the number of times that m minus w remains at. When does the maximum increase? Well, only when you're currently at the maximum and you choose to move up, which means that m minus w is 0, and after one step, m minus w remains the same. So this argues that the maximum is equal to the amount of time that m minus w stays at 0, which is exactly a local time of this walk. So this argues that the local time has the same distribution as the maximum of a random walk. So this was all for random walks. Then there was a few kind of small imprecisions there, but when you translate to Brownian motion, all of that becomes exact, and the statement of Levy's theorem follows. So, Eddie, I think you're saying something, but I do not hear you.
Minutes.
Oh, now I hear you.
You have 5 minutes.
Eddie? You have 5 minutes. I have 5 minutes. Great.
5 minutes.
Yes, I hear you.
Good.
Okay, so this argument gives you a characterization of how much time Brownian motion spends at any one point, right? Not just the mean, but all the moments and so on. So let's look at this problem of Hamming weight with a spike and try to apply it. Let's say the spike has width n to the a and height n to the b. I think Elizabeth might have used the opposite parameters, but let's use these. So how does the quantum algorithm perform? We know that if a plus b is less than a half, the adiabatic gap remains constant. There's an intermediate regime where the adiabatic gap goes down polynomially, and if a and b are too large, the gap goes down exponentially. And this is due to Farhi, Goldstone, Gutman. There's an argument by Reichardt, then Kong and Crossan, Brady Van Dam, and then Jiang et al. All have done some version of this argument. So let's see how these arguments about Brownian motion can apply here. So if we have this spike, what this corresponds to is some region that when the Brownian motion traverses, it effectively gets penalized. So when you're in this region, you incur an energy penalty and your probability gets suppressed. And we know that if there was no spike, the distribution would be just Brownian motion. And so we can exactly characterize the what we call the spike time, which is a fraction of time you spend on the spike, which goes like a Gaussian, or sorry, the absolute value of a Gaussian with this standard deviation of n to the a minus 1/2. And you can prove it using Levy's theorem, as I've kind of outlined, or in my paper with Elizabeth, we prove it by mapping it back to the quantum system, arguing that properties of the classical system should correspond to properties of the quantum system. And then what this implies is essentially that typical paths in this a plus b less than 1/2 region don't notice the spike. And the reason is something called the Feynman-Koch theorem, but it's almost elementary. It just says that the probability of your path, actually, sorry, I left off a normalization. The probability of a path with a spike is proportional to the probability of path without the spike, just reweighted by the penalty from the spike. And if you look at how much time you're likely to spend on the spike and multiply it by the penalty, then in this a plus b less than half regime, typically you're just not going to have very much of a penalty. So that, you could say, is the intuition behind the result that you saw the actual proof of in Elizabeth's talk. Let me now talk about how we might go beyond that to a regime where our analysis doesn't yet cover, but I think should be able to, and which relates to the instantons that Jiang et al. Will talk about tomorrow. So if you're in this regime where 2a plus b is less than 1, but our other proof doesn't apply, then what can we say? Well, talking about using Brownian motion, we know that to traverse a region of width n to the a, the number of steps you need is like the square of that width. That's because to get some distance d with Brownian motion, it takes d squared steps. And so the typical number of steps to traverse the spike and if you follow through how much is the probability reduced by, you get this factor here, exponential minus n to the 2a plus b minus 1. And what that means is that 2a plus b less than equal to 1 is the threshold to cross the spike once. So if you cross the spike once, you incur a penalty, which looks like e to the minus that quantity. So if that quantity is much more than 1, you're unlikely to ever cross the spike. If it's less than 1, then you're typically able to cross the spike at least a constant number of times. And so that argues that this threshold is what basically when the state space becomes disconnected, the state space becomes disconnected once 2a plus b is greater than 1, and it's roughly connected when 2a plus b is less than 1. And you can get that using these arguments about random walks. So I'm about out of time. I think Elizabeth sort of talked about canonical paths and flow, so I don't say too much about it. But just very briefly, the conductance of a distribution is basically the worst bottleneck, right? Which Elizabeth mentioned. And how does our rigorous proof differ from the more powerful results that you get using instantons? I would argue that our proof is based on these canonical paths or canonical flows, which imply that there is no bad cut. Whereas if you do an analysis based on instantons, it implies that a plausible cut, one that is physically justified, does not have too bad of a gap. So what I presented back in this slide is that it kind of rules out a certain plausible cut. And what we'd like to do next is extend this to argue, to construct a set of canonical flows or canonical paths that implies that there's no cut. Okay, so let me conclude. So what are the key open questions here? I think what we've covered so far is this toy problem of a bit symmetric case, which of course is an easy problem. We'd like to go to the multidimensional case, which is the more interesting one. And the approach that Elizabeth outlined in the case of a plus b less than a half basically generalizes to whenever the unperturbed problem has a good set of canonical paths, and the perturbation is small relative to the quantum gap. In that case, it means that the ground state wave function doesn't change very much, and that the paths will not have their probability shifted too much by the perturbation. But this other scenario of 2a plus b less than 1, I think that generalizes to the case when your ground state does change a lot, but it's still possible to traverse the spike once without too much penalty. And I think it'd be quite interesting to kind of get a general proof for that scenario. Another open question, which I think I was trying to start to address by looking at the state space of these paths, is how does this geometry of the quantum state relate to the quantum state of quantum Monte Carlo? We know, I think I learned this from Wim van Dam, that ground states of gapped Hamiltonians have high conductance. So there's no good bottleneck for the ground state distribution of a gapped Hamiltonian. But what can we say about the implications of this for paths in quantum Monte Carlo? Does it imply that paths also have good conductance? That may or may not be true. And finally, the big question is whether there's a polytime simulation of adiabatic quantum computing or an exponential simulation. I think that's very much open. Okay, so
thank you.
Thanks for your attention. I can take questions now.
Okay, well, we can clap. Oh, okay, we're going to have some questions, I guess. Who would like to ask a question? Okay, in the front row, we have a question.
Hello. So,
you have to talk into the mic.
Oh, yes. So, you can hear me?
Yes.
At one point, you said that you do not know of any adiabatic algorithms for factoring numbers. And I'd just like to say that such an algorithm does exist. And some numbers have been factored experimentally using NMR-based adiabatic quantum computation. And those numbers are larger than what's been factored using Shor's algorithm so far. RSA 220 requires a few thousand qubits. The problem there is that there's multi-qubit interactions, 4-qubit interactions, so they can't fit on D-Wave yet. The other thing I wanted to say was about the boson sampling. In your table, you said that the boson sampling has no useful applications. And so about that, I would like to ask, what about the paper by Alanis Buruguzic's group on using boson sampling for determining Frank-Condon factors in chemical systems.
Okay, thanks for the comments. I have not done my homework and I have not read that paper, and so I should do that and give an opinion about it. So so it may be that actually, yeah, that I may have to change that part of the slide. As for the adiabatic factoring algorithm, I guess I would say that it's not proved to run in polynomial time, and it does not seem to take advantage of the, well, since it does not use the methods of Shor's algorithm, it seems to me that it does not seem to me likely that it would do better than it would for a general constraint satisfaction problem. So I guess my conjecture is that algorithm will not run in polynomial time. But I guess it's, that's just my opinion,
Yes,
and
okay.
I could well be wrong about it.
You're right.
And I
Thank
guess
you.
all we can see is not proved either way.
Okay, let's look for more questions. Okay, well, that's okay, because we're running behind. So, Aram, we're going to cut you off. Thank you very much.
Thank you.